Let's take a look at projectile motion, section 12-6. This is anytime that something's flying through the air. Doesn't have to be air. We're going to ignore the fact that it's in air in most of these problems, or ignore drag. I'll go over that. But it's any time when the only force is gravity acting on it, and we have some initial trajectory with some initial velocity. So some mass is getting projected at some velocity at some angle theta. And the general case for this would look something like this. And we could say that we launch something, and if we follow the path, it would be that of a parabola. But we need to break this up into components. We need to look up what happens in the y direction and what happens in the x direction. If we take a mass and shoot it out of something like a cannon or a gun or a catapult or kick a ball, there's all kinds of different ways we could create a projectile. We typically have some initial velocity vector and some angle theta. Alright, I'm going to trace the projectile path, and then we're going to draw some points on there. So what's very important to note is, one, that this vector v0 that I just drew can be broken up into x components and y components, and we will have to do that. So it has some initial x velocity. As it moves through time and through space, it maintains that same x velocity. So the vector length in the x direction does not change unless it's subject to drag or something. So we can say that the velocity in the x direction is constant. That's not the case for the velocity in the y direction, though. It's definitely not constant, because the whole point of this chapter is that we are under the influence of gravity. So whatever initial velocity vector it has in the y direction, that thing is going to shrink. So right now it looks something like this. It's going to keep getting smaller and smaller until it's 0 and starts turning around the other way. And then it'll, if it returns to the same level, it will have the same magnitude going down as it did when it was projected up. Okay, so we can say that the velocity in the y direction is 0 up at the top of the projectile, and if it returns to the same level, this is half of the flight time, and this is half of the flight time right here. If it doesn't return to the same level, we can't say that, and it doesn't return to the same level of these velocity vectors right here, will not be the same magnitude either. Okay, so that means we need to take these velocity vectors and break them up. Any problem that involves a projectile motion, we need to look at the velocity in the x direction independently. That would be the magnitude of v. You can put the whole thing. V times the cosine of this angle right here. And the velocity in the y direction would be equal to v times the sine of that angle. And we need to break up into these components before we start the problem. Okay, now since we're only dealing with acceleration in one direction, that's the y direction, and that acceleration is due to gravity, we can use constant acceleration equations. So we derived these previously, and these were derived in rectangular coordinates, so take note, I guess. We typically do projectile problems in rectangular or Cartesian coordinates. Coordinates. We are typically going to neglect air resistance unless it says so. If not, the force due to drag is typically a function of velocity. What else? Very important, the only force acting is the force due to gravity. Okay, when doing these problems in any dynamics problem, I was taught by my teacher to do this, to say, one, is anything touching it? And we're not working with forces yet, but is anything touching it? Because if it is, that could be giving a force. Anything touching it. And two, is gravity in the picture? That's all we need to work with for dynamics in this class. So is something touching it? Is friction touching it? Is a force applied? Is there tension on it? And is gravity in the picture? So when we do free body diagrams, we're going to do it as such. Okay, let's move on to our constant acceleration equations. You've definitely seen these before. So constant accel. Our generic equations are that the velocity final was equal to v naught plus acceleration constant times time. We also had that x final was equal to x initial, or x naught, plus v naught in times time, plus 1/2 the acceleration times time squared. And then we had the time independent equation that we derived, v final squared is equal to v naught, go ahead and change that to naught, squared plus 2 times the acceleration times delta s, whatever dimension we might be in. So 1, 2, and 3. Okay, in high school, I think they get you to make big old tables for which equation to use in which direction. We use these same equations for x and y. Just if you're doing x, you get to cross out the gravity terms, right? If you're doing y, put g in, put acceleration as g. So, get rid of those real quick. Let's see how that works. So if we're looking just the x direction, that would be horizontal motion. And I mentioned that in that case, the velocity in the x direction is constant. There's no forces acting unless there's drag to slow it down. So it just keeps cruising. It's a Newton's first law thing. It maintains its velocity, and if by crossing this out, you see velocity final ends up equaling velocity initial. By crossing this out, you get another equation that tells you the same thing, that we maintain velocity as it travels through space. And okay, since the velocity is constant, we can say the acceleration in the x direction is equal to 0. And that makes our first equation just the velocity final in the x direction is equal to the velocity initial in the x direction. And then we had this plus the acceleration in the x direction times time, but that's equal to 0. So we just proved, boom, that the velocity is constant. If there's no acceleration in the x direction, we can predict how far it goes using x final is equal to x initial plus v naught in the x direction. You would put your component v cosine theta in there times time, plus I'm going to go ahead and write it, 1/2 acceleration in the x times time squared. The acceleration in the x is 0, so this whole term goes away. We're just left with if you're traveling at this velocity for this amount of time, you're going to move this distance. Alright, then we have, I already did this one, but we'll write it down. Vf in the x direction squared is equal to v initial in the x direction squared plus 2 times the acceleration in the x direction times delta, I guess x in this case. Once again, this is 0, so we just proved that the velocity is constant in its space as it travels. However, we gotta look in the vertical direction, vertical motion. We can't cross those terms out. We literally have to say velocity final in the y direction is equal to velocity initial in the y direction plus the acceleration, in this case acceleration is gravity, so we'll say plus gravity times time. And we'll typically use gravity as a 9.81 meters per second squared, or 32.2 feet per second squared. And I don't necessarily put a plus or minus in. In this case, we would put a minus sign in. I typically will just go off my free body diagram, and we'll learn that in chapter 13. If we have weight mg pointed down and I sum my forces, I'm going to call that a minus mg, and just put a positive 9.8 in for g. I will teach you those tricks. In this case, we would need to put a negative 9.81 in there to calculate some stuff. The next one is y final is equal to y initial plus v naught in the y direction plus 1/2 gravity times time squared. So it's another constant acceleration, but we have gravity. And then v final in the y direction squared is equal to v naught in the y direction squared plus 2 times gravity times delta y. So if we have constant acceleration, we can use these equations right here. And I don't think it's worth memorizing this equation and this equation and this. Memorize 3 equations and cross out the stuff you don't need. So if there's no acceleration in the x direction, just cross it out. If you're looking at the y direction and we're dealing with gravity, then don't cross out the gravity term. Just analyze it. If it's a projectile, velocity in the x is constant. If it's a projectile, the velocity in the y direction is under the influence of gravity. So I only remember the 3 equations, and then I cross out what I don't need. It gets really tedious. I see some crazy note cards, pretty much is all I'm getting at. You don't need to remember 9 equations, there's only 3. Alright.